Hello, ladies and gentlemen. A happy Monday to you. Hope you guys are doing well. So, rewinding a little bit of what we talked about last week, we started talking about acids and bases and the kind of fun you can come up with, and I gave you guys some quiz questions to be thinking about. Um, Largely, we talked about the different models of acids and bases, whether it was the Lewis, the Bronsted-Lowry, all of that jazz. So with that in mind, we're going to talk a little bit about equilibria, which is plural for equilibrium. Namely, today we're going to be talking about water. And this should be a very short lesson today. Um, Yay, said all the students. So, real quick, the first thing I wanted to talk about was, before we take notes, when you think about something as being acidic or basic, right? What's a very acidic food that you can think of? Um, One that I can think of right off the bat would be maybe tomato juice or orange juice. Um, some things you can eat, and it's fantastic. Other things, not so much. Like what about hydrochloric acid? Do you really want to throw that in your mouth? Or one thing I wrote down was what was it called? I think it was pen perchloric acid, where if it touches cloth, it'll literally explode. Which I wish I could do as an experiment. I'm going to start doing some experiments on camera, probably starting next week, so you guys can see them, and maybe even get some experience that you could do at home. But anyway, that's super acidic, so acidic that it explodes when it touches cloth, which is pretty ridiculous. So, what's the difference there? What's going on? How is orange juice different than perchloric acid? Why is one more acidic than the other? And the difference really comes down to what we talked about yesterday. How willing is your acid to give up or take a proton from something else? How willing is your base to take or give away a proton to something else? And that willingness of that acid or base completely decides whether or not that is going to be really acidic or really not acidic. So, how we're going to explain this is through something called the self ionization of water, which is pretty crazy. I had to read this section a couple times to really figure out what the heck was going on because it's weird, but it's really cool. Basically, water at all times is having many acid-base chemical reactions with itself. If you think back to what we learned in probably physical science or middle school science, what's the pH of pure water? 7. It's right in the middle, right? The pH of water, it's not acidic and it's not basic. Well, when you look deep down enough, it's actually both. And the fact that it's both means it's balancing and canceling each other out. Let me show you. So the self-ionization of water, this basically means that it reacts with itself constantly. And this is how. Here is our equation. So you've got a little water, it's a liquid, plus a little bit of water, it's also a liquid. And there's a reaction, which if you didn't know, these little arrows mean there's a reaction, or namely one that could go either way. Um, and what's being created is an hydronium, which should be aqueous, and a a hydroxide, which is aqueous. And I said it's creating, but really what's happening is these two waters are reacting, bam. One of them gives the H to the other one. And then these things say, hang on a second, this isn't how we're supposed to be, so they switch back and then bam, they're back in the water. And then they flip over here, and then they flip back here, and then they flip over here. They're constantly trading that H around. And there's a diagram in the book that I very much like. So I'm going to draw it real quick. Um, You had two little hydrogens on an oxygen. Then you had two little hydrogens on an oxygen. They're having that reaction, and then you have Mr. Acid, who's hogging all those protons to himself, all those hydrogens. Um, and then you end up having your little base, who's just stuck with one little one. So that's what's happening chemically. One of those little protons is being thrown onto the other one, and then they end up unbalanced. Kind of weird stuff. And as you recall, basically the more protons and hydrogens your element has, or your compound has, the more acidic it's going to be. So you have weak acid, weak base, back to normal. Weak acid, weak base, back to normal. Kind of weird, kind of weird. So this all, okay, this reaction can be described with something called the ionization constant. Back to constants again. The ionization constant of water. The ionization constant of water. And in your homework from Friday, you should have come across this term when I asked you what the heck that 1.0 times 10 to the negative 7 was. That's the ionization constant of water. So we have an equation. The book does it in 2 steps. I'm just going to give it to you in 1 because I don't see the point. We have an equation, okay? An equation that uses this ionization constant. And here it is. Your hydronium times your hydroxide equals that. Okay? This equals that times that. That's our equation. Which means that technically we should be able to rearrange it, but we'll leave that for later. So, our constant, right? What is our ionization constant of water? Well, something we need to know is the concentration in this reaction, right? There's a certain amount of water and a certain amount of hydroxide and a certain amount of hydronium. The concentration of hydronium and hydroxide are 1.0 times 10 to the negative 7 moles per liter. And what's moles per liter? Molar. So you could also write this with, or a capital M. Usually it'll be in capital M. That's the concentration of our pieces. So we could rewrite this as our equation equals 1.0 times 10 to the negative 7. That's the concentration of the hydronium times the concentration of the hydroxide. And if there's any chance that you remember from math what you do to exponents when you multiply them together, you add them, then you would end up with 1.0 times 10 to the negative 14. And this is our ionization constant. Okay? So, I would like to show you guys how this can be applied. Alrighty, so I'm about to go through a problem on page 414, and then I will give you 2 similar problems so you can practice on your own. This is very easy compared to what we did last section. So, our little equation was our concentration constant equals our hydroxide, or our hydronium, times our hydroxide. Right? Our acid and our base. Balancing each other out. So it says the concentration of hydronium ions, you got to keep those words straight. Hydronium ions is found to be 5.10 to the negative 7 moles per liter. What's the concentration of OH ions? Okay, so I need to find my OH ions. Cool. So, what can I plug in here? I'm looking for this, right? I'm looking for my hydroxide. So how do I get hydroxide on the one side of the equation? Well, if I use a hint from math, I know that if I want to get something to the other side, I have to do the opposite of the I have to do the opposite of what I see. I see multiplication, and I want to get OH. I want to get H3O away from OH because I want OH by itself. So I'm going to divide both sides by H3O plus, by my hydronium. That way these cancel out, and I am left with OH minus equals my concentration constant, my ionization constant of water, over H3O plus. Great. So now that I have this set up, let's plug in my numbers. I'm looking for my OH. What's my ionization constant for water? Well, it's supposed to be always for water at I believe, 25 degrees Celsius. We're just going to assume it's basically STP. It's 1.0 times 10 to the negative 14 over, what did they give me? H3O? 5 times 10 to the negative 7. So, if I plug these two numbers in to a calculator, and then I solve, I should get my answer. And what I get is 2.0 times 10 to the negative 4. And there's the concentration I'm looking for. It's that simple. So, with that being said, I have two more problems. Please pay attention to what I'm asking you for. And there's definitely not going to be a question on your quiz that looks just like one of these two problems. I definitely won't be asking you what the ionization constant of water is. So there you go. Um, with that being said, good luck on your homework. If you have any questions about today, let me know. But I will see you guys tomorrow to talk about the pH scale. And good luck on your quiz. Bye.